Chapter 1. Introduction. Designing object-oriented software is hard, and designing reusable object-oriented software is even harder. You must find pertinent objects, factor them into classes at the right granularity, define class interfaces and inheritance hierarchies, and establish key relationships among them. Your design should be specific to the problem at hand but also general enough to address future problems and requirements. You also want to avoid redesign, or at least minimize it. Experienced object-oriented designers will tell you that a reusable and flexible design is difficult if not impossible to get right the first time. Before a design is finished, they usually try to reuse it several times, modifying it each time. Yet experienced object-oriented designers do make good designs. Meanwhile, new designers are overwhelmed by the options available and tend to fall back on non-object-oriented techniques they've used before. It takes a long time for novices to learn what good object-oriented design is all about. Experienced designers evidently know something inexperienced ones don't. What is it? One thing expert designers know not to do is solve every problem from first principles. Rather, they reuse solutions that have worked for them in the past. When they find a good solution, they use it again and again. Such experience is part of what makes them experts. Consequently, you'll find recurring patterns of classes and communicating objects in many object-oriented systems. These patterns solve specific design problems and make object-oriented designs more flexible, elegant, and ultimately reusable. They help designers reuse successful designs by basing new designs on prior experience. A designer who is familiar with such patterns can apply them immediately to design problems without having to rediscover them. An analogy will help illustrate the point. Novelists and playwrights rarely design their plots from scratch. Instead, they follow patterns like tragically flawed hero, Macbeth, Hamlet, etc., or the romantic novel, countless romance novels. In the same way, object-oriented designers follow patterns like represent states with objects and decorate objects so you can easily add, remove features. Once you know the pattern, a lot of design decisions follow automatically. We all know the value of design experience. How many times have you had design déjà vu, that feeling that you've solved the problem before but not knowing exactly where or how? If you could remember the details of the previous problem and how you solved it, then you could reuse the experience instead of rediscovering it. However, we don't do a good job of recording experience in software design for others to use. The purpose of this book is to record experience in designing object-oriented software as design patterns. Each design pattern systematically names, explains, and evaluates an important and recurring design in object-oriented systems. Our goal is to capture design experience in a form that people can use effectively. To his end, we have documented some of the most important design patterns and present them as a catalog. Design patterns make it easier to reuse successful designs and architectures. Expressing proven techniques as design patterns makes them more accessible to developers of new systems. Design patterns help you choose design alternatives that make a system reusable and avoid alternatives that compromise reusability. Design patterns can even improve the documentation and maintenance of existing systems by furnishing an explicit specification of class and object interactions and their underlying intent. Put simply, design patterns help a designer get a design right faster. None of the design patterns in this book describes new or unproven designs. We have included only designs that have been applied more than once in different systems. Most of these designs have never been documented before. They are either part of the folklore of the object-oriented community or are elements of some successful object-oriented systems, neither of which is easy for novice designers to learn from. So although these designs aren't new, we capture them in a new and accessible way, as a catalog of design patterns having a consistent format. Despite the book's size, the design patterns in it capture only a fraction of what an expert might know. It doesn't have any patterns dealing with concurrency or distributed programming or real-time programming. It doesn't have any application domain-specific patterns. It doesn't tell you how to build user interfaces, how to write device drivers, or how to use an object-oriented database. Each of these areas has its own patterns, and it would be worthwhile for someone to catalog those too. 1.1 What is a design pattern? Christopher Alexander says, each pattern describes a problem which occurs over and over again in our environment, and then describes the core of the solution to that problem, in such a way that you can use this solution 1,000,000 times over, without ever doing it the same way twice. AIS plus 77, page X. Even though Alexander was talking about patterns in buildings and towns, what he says is true about object-oriented design patterns. Our solutions are expressed in terms of objects and interfaces instead of walls and doors, but at the core of both kinds of patterns is a solution to a problem in a context. In general, a pattern has 4 essential elements. 1. The pattern name is a handle we can use to describe a design problem, its solutions, and consequences in a word or two. Naming a pattern immediately increases our design vocabulary. It lets us design at a higher level of abstraction. Having a vocabulary for patterns lets us talk about them with our colleagues, in our documentation, and even to ourselves. It makes it easier to think about designs and to communicate them and their trade-offs to others. Finding good names has been one of the hardest parts of developing our catalog. 2. The problem describes when to apply the pattern. It explains the problem and its context. It might describe specific design problems such as how to represent algorithms as objects. It might describe class or object structures that are symptomatic of an inflexible design. Sometimes the problem will include a list of conditions that must be met before it makes sense to apply the pattern. 3. The solution describes the elements that make up the design, their relationships, responsibilities, and collaborations. The solution doesn't describe a particular concrete design or implementation, because a pattern is like a template that can be applied in many different situations. Instead, the pattern provides an abstract description of a design problem and how a general arrangement of elements, classes and objects in our case, solves it. 4. The consequences are the results and trade-offs of applying the pattern, though consequences are often unvoiced when we describe design decisions. They are critical for evaluating design alternatives and for understanding the costs and benefits of applying the pattern. The consequences for software often concern space and time trade-offs. They may address language and implementation issues as well. Since reuse is often a factor in object-oriented design, the consequences of a pattern include its impact on a system's flexibility, extensibility, or portability. Listing these consequences explicitly helps you understand and evaluate them. Point of view affects one's interpretation of what is and isn't a pattern. One person's pattern can be another person's primitive building block. For this book we have concentrated on patterns at a certain level of abstraction. Design patterns are not about designs, such as linked lists and hash tables that can be encoded in classes and reused as is. Nor are they complex, domain-specific designs for an entire application or subsystem. The design patterns in this book are descriptions of communicating objects and classes that are customized to solve a general design problem in a particular context. A design pattern names, abstracts, and identifies the key aspects of a common design structure that make it useful for creating a reusable object-oriented design. The design pattern identifies the participating classes and instances, their roles and collaborations, and the distribution of responsibilities. Each design pattern focuses on a particular object-oriented design problem or issue. It describes when it applies, whether it can be applied in view of other design constraints, and the consequences and trade-offs of its use. Since we must eventually implement our designs, a design pattern also provides sample C++ and, sometimes, Smalltalk code to illustrate an implementation. Although design patterns describe object-oriented designs, they are based on practical solutions that have been implemented in mainstream object-oriented programming languages like Smalltalk and C++ rather than procedural languages, Pascal, C, Ada, or more dynamic object-oriented languages, Class, Dylan, Self. We chose Smalltalk and C++ for pragmatic reasons. Our day-to-day experience has been in these languages, and they are increasingly popular. The choice of programming language is important because it influences one's point of view. Our patterns assume Smalltalk/C++ level language features, and that choice determines what can and cannot be implemented easily. If we assumed procedural languages, we might have included design patterns called inheritance, encapsulation, and polymorphism. Similarly, some of our patterns are supported directly by the less common object-oriented languages. In fact, there are enough differences between Smalltalk and C++ to mean that some patterns can be expressed more easily in one language than the other. 1.2 Design patterns in Smalltalk MVC. The model/view/controller MVC triad of classes, KP88, is used to build user interfaces in Smalltalk 80. Looking at the design patterns inside MV should help you see what we mean by the term pattern. MVC consists of three kinds of objects. The model is the application object, the view is its screen presentation, and the controller defines the way the user interface reacts to user input. Before MVC, user interface designs tended to lump these objects together. MVC decouples them to increase flexibility and reuse. MVC decouples views and models by establishing a subscribe/notify protocol between them. A view must ensure that its appearance reflects the state of the model. Whenever the model's data changes, the model notifies views that depend on it. In response, each view gets an opportunity to update itself. This approach lets you attach multiple views to a model to provide different presentations. You can also create new views for a model without rewriting it. The following diagram shows a model and three views. We've left out the controllers for simplicity. The model contains some data values, and the views defining a spreadsheet, histogram, and pie chart display these data in various ways. The model communicates with its views when its values change, and the views communicate with the model to access these values. Taken at face value, this example reflects a design that decouples views from models, but the design is applicable to a more general problem, decoupling objects so that changes to one can affect any number of others without requiring the changed object to know details of the others. This more general design is described by the observer, page 293. Design pattern. Another feature of MVC is that views can be nested. For example, a control panel of buttons might be implemented as a complex view containing nested button views. The user interface for an object inspector can consist of nested views that may be reused in a debugger. MV supports nested views with the Composite view class, a subclass of view. Composite view objects act just like view objects. A composite view can be used wherever a view can be used, but it also contains and manages nested views. Again, we could think of this as a design that lets us treat a composite view just like we treat one of its components, but the design is applicable to a more general problem, which occurs whenever we want to group objects and treat the group like an individual object. This more general design is described by the Composite 163 design pattern.it. Lets you create a class hierarchy in which some subclasses define primitive objects, e.g., button, and other classes define composite objects, composite view, that assemble the primitives into more complex objects. MVC also lets you change the way a view responds to user input without changing its visual presentation. You might want to change the way it responds to the keyboard, for example, or have it use a pop-up menu instead of command keys. MVC encapsulates the response mechanism in a controller object. There is a class hierarchy of controllers, making it easy to create a new controller as a variation on an existing one. A view uses an instance of a controller subclass to implement a particular response. Strategy. To implement a different strategy, simply replace the instance with a different kind of controller. It's even possible to change a view's controller at runtime to let the view change the way it responds to user input. For example, a view can be disabled so that it doesn't accept input simply by giving it a controller that ignores input events. The view-controller relationship is an example of the strategy 315 design pattern. A strategy is an object that represents an algorithm. It's useful when you want to replace the algorithm either statically or dynamically, when you have a lot of variants of the algorithm, or when the algorithm has complex data structures that you want to encapsulate. MVC uses other design patterns, such as factory method 107, to specify the default controller class for a view, and decorator 175, to add scrolling to a view. But the main relationships in MVC are given by the observer, composite, and strategy design patterns. 1.3 Describing design patterns. How do we describe design patterns? Graphical notations, while important and useful, aren't sufficient. They simply capture the end product of the design process as relationships between classes and objects. To reuse the design, we must also record the decisions, alternatives, and trade-offs that led to it. Concrete examples are important. 2. Because they help you see the design in action. We describe design patterns using a consistent format. Each pattern is divided into sections according to the following template. The template lends a uniform structure to the information, making design patterns easier to learn, compare, and use. Pattern name and classification. The pattern's name conveys the essence of the pattern succinctly. A good name is vital, because it will become part of your design vocabulary. The pattern's classification reflects the scheme we introduce in section 1.5. Intent. A short statement that answers the following questions. What does the design pattern do? What is its rationale and intent? What particular design issue or problem does it address? Also known as other well-known names for the pattern, if any. Motivation. A scenario that illustrates a design problem and how the class and object structures in the pattern solve the problem. The scenario will help you understand the more abstract description of the pattern that follows. Applicability. What are the situations in which the design pattern can be applied? What are examples of poor designs that the pattern can address? How can you recognize these situations? Structure. A graphical representation of the classes in the pattern using a notation based on the object modeling technique, OMT, RBP +91. We also use interaction diagrams, JCJ092, BO94, to illustrate sequences of requests and collaborations. Between objects, Appendix B describes these notations in detail. Participants. The classes and/or objects participating in the design pattern and their responsibilities. Collaborations. How the participants collaborate to carry out their responsibilities. Consequences. How does the pattern support its objectives? What are the trade-offs and results of using the pattern? What aspect of system structure does it let you vary independently? Implementation. What pitfalls, hints, or techniques should you be aware of when implementing the pattern? Are there language-specific issues? Sample code. Code fragments that illustrate how you might implement the pattern in C++ or Smalltalk. Known uses. Examples of the pattern found in real systems. We include at least 2 examples. From different domains. Related patterns. What design patterns are closely related to this one? What are the important differences? With which other patterns should this one be used? The appendices provide background information that will help you understand the patterns and the discussion surrounding them. Appendix A is a glossary of terminology we use. We've already mentioned Appendix B, which presents the various notations. We'll also describe aspects of the notations as we introduce them in the upcoming discussions. Finally, Appendix C contains source code for the foundation classes We1 for the catalog of design patterns. The catalog beginning on page 79 contains 23 design patterns. Their names and intents are listed next to give you an overview. The number in parentheses after each pattern. Name gives the page number for the pattern, a convention we follow throughout the book. Abstract Factory, 87, provide an interface for creating families off-related or dependent objects without specifying their concrete classes. Adapter, 139, convert the interface of a class into another interface clients expect. Adapter lets classes work together that couldn't otherwise because of incompatible interfaces. Bridge, 151, decouple an abstraction from its implementation so that the two can vary independently. Builder, 97, separate the construction of a complex object from its representation so that the same construction process can create different representations. Chain of responsibility, 223, avoid coupling the sender of a request to its receiver by giving more than one object a chance to handle the request. Chain the receiving objects and pass the request along the chain until an object handles it. Command, 233, encapsulate a request as an object, thereby letting you parameterize clients with different requests, queue or log requests, and support undoable operations. Composite, 163, compose objects into tree structures to represent part-whole hierarchy as. Composite lets clients treat individual objects and compositions of objects uniformly. Decorator, 175, attach additional responsibility to an object dynamically. Decorators provide a flexible alternative to subclassing for extending functionality. Facade, 185, provide a unified interface to a set of interfaces in a subsystem. Facade defines a higher-level interface that makes the subsystem easier to use. Factory method, 107, define an interface for creating an object, but let subclasses decide which class to instantiate. Factory method lets a class defer instantiation to subclasses. 1.5 Organizing the catalog. Design patterns vary in their granularity and level of abstraction. Because there are many design patterns, we need a way to organize them. This section classifies design patterns so that we can refer to families of related patterns. The classification helps you learn the patterns in the catalog faster, and it can direct efforts to find new patterns as well. We classify design patterns by two criteria. Table 1.1, the first criterion, called purpose, reflects what a pattern does. Patterns can have either creational, structural, or behavioral purpose. Creational patterns concern the process of object creation. Structural patterns deal with the composition of classes or objects. Behavioral patterns characterize the ways in which classes or objects interact and distribute responsibility. The second criterion, called scope, specifies whether the pattern applies primarily to classes or to objects. Class patterns deal with relationships between classes and their subclasses. These relationships are established through inheritance, so they are static, fixed at compile time. Object patterns deal with object relationships, which can be changed at runtime and are more dynamic. Almost all patterns use inheritance to some extent. So the only patterns labeled class patterns are those that focus on class relationships. Note that most patterns are in the object scope. Creational class patterns defer some part of object creation to subclasses, while creational object patterns defer it to another object. The structural class patterns use inheritance to compose classes, while the structural object patterns describe ways to assemble objects. The behavioral class patterns use inheritance to describe algorithms and flow of control, whereas the behavioral object patterns describe how a group of objects cooperate to perform a task that no single object can carry out alone. There are other ways to organize the patterns. Some patterns are often used together. For example, composite is often used with iterator or visitor. Some patterns are alternatives. Prototype is often an alternative to abstract factory. Some patterns result in similar designs even though the patterns have different intents. For example, the structure diagrams of Composite and Decorator are similar. Yet another way to organize design patterns is according to how they reference each other in their related patterns sections. Figure 1.1 depicts these relationships graphically. Clearly there are many ways to organize design patterns. Having multiple ways of thinking about patterns will deepen your insight into what they do, how they compare, and when to apply them. 1.6 How design patterns solve design problems. Design patterns solve many of the day-to-day problems object-oriented designers face, and in many different ways. Here are several of these problems and how design patterns solve them. Finding appropriate objects. Object-oriented programs are made up of objects. An object packages both data and the procedures that operate on that data. The procedures are typically called methods or operations. An object performs an operation when it receives a request or message from a client. Requests are the only way to get an object to execute an operation. Operations are the only way to change an object's internal data. Because of these restrictions, the object's internal state is said to be encapsulated, it cannot be accessed directly, and its representation is invisible from outside the object. The hard part about object-oriented design is decomposing a system into objects. The task is difficult because many factors come into play: encapsulation, granularity, dependence, flexibility, performance, evolution, reusability, and on and on. They all influence the decomposition, often in conflicting ways. Object-oriented design methodologies favor many different approaches. You can write a problem statement, single out the nouns and verbs, and create corresponding classes and operations. Or you can focus on the collaborations and responsibilities in your system. Or you can model the real world and translate the objects found during analysis into design. There will always be disagreement on which approach is best. Many objects in a design come from the analysis model. But object-oriented designs often end up with classes that have no counterparts in the real world. Some of these are low-level classes like arrays. Others are much higher level. For example, the Composite 163 pattern introduces an abstraction for treating objects uniformly that doesn't have a physical counterpart. Strict modeling of the real world leads to a system that reflects today's realities but not necessarily tomorrow's. The abstractions that emerge during design are key to making a design flexible. Design patterns help you identify less obvious abstractions and the objects that can capture them. For example, objects that represent a process or algorithm don't occur in nature, yet they are a crucial part of flexible designs. The Strategy 315 pattern describes how to implement interchangeable families of algorithms. The State 305 pattern represents each state of an entity as an object. These objects are seldom found during analysis or even the early stages of design. They're discovered later in the course of making a design more flexible and reusable. Determining object granularity. Objects can vary tremendously in size and number. They can represent everything, down to the hardware or all the way up to entire applications. How do we decide what should be an object? Design patterns address this issue as well. The Facade 185 pattern describes how to represent complete subsystems as objects, and the Flyweight 195 pattern describes how to support huge numbers of objects at the finest granularities. Other design patterns describe specific ways of decomposing an object into smaller objects, abstract. Factory 87 and Builder 97 field objects whose only responsibilities are creating other objects. Visitor 331 and Command 233 yield objects whose only responsibilities are to implement a request on another object or group of objects. Specifying object interfaces. Every operation declared by an object specifies the operation's name, the objects it takes as parameters, and the operation's return value. This is known as the operation's signature. The set of all signatures defined by an object's operations is called the interface to the object. An object's interface characterizes the complete set of requests that can be sent to the object. Any request that matches a signature in the object's interface may be sent to the object. A type is a name used to denote a particular interface. We speak of an object as having the type window if it accepts all requests for the operations defined in the interface. Named window. An object may have many types, and widely different objects can share a type. Part of an object's interface may be characterized by one type, and other parts by other types. Two objects of the same type need only share parts of their interfaces. Interfaces can contain other interfaces as subsets. We say that a type is a subtype of another if its interface contains the interface of its supertype. Often we speak of a subtype inheriting the interface of its supertype. Interfaces are fundamental in object-oriented systems. Objects are known only through their interfaces. There is no way to know anything about an object or to ask it to do anything without going through its interface. An object's interface says nothing about its implementation. Different objects are free to implement requests differently. That means two objects having completely different implementations can have identical interfaces. When a request isn't to an object, the particular operation that's performed depends on both the request and the receiving object. Different objects that support identical requests may have different implementations of the operations that fulfill these requests. The Runtime association of a request to an object and one of its operations is known as dynamic binding. Dynamic binding means that issuing a request doesn't commit you to a particular implementation until runtime. Consequently, you can write programs that expect an object with a particular interface, knowing that any object that has the correct interface will accept the request. Moreover, dynamic binding lets you substitute objects that have identical interfaces for each other at runtime. This substitutability is known as polymorphism, and it's a key concept in object-oriented systems. It lets a client object make few assumptions about other objects beyond supporting a particular interface. Polymorphism simplifies the definitions of clients, decouples objects from each other, and lets them vary their relationships to each other at runtime. Design patterns help you define interfaces by identifying their key elements and the kinds of data that get sent across an interface. A design pattern might also tell you what not to put in the interface. The Memento 283 pattern is a good example. It describes how to encapsulate and save the internal state of an object so that the object can be restored to that state later. The pattern stipulates that Memento objects must define two interfaces, a restricted one that lets clients hold and copy mementos, and a privileged one that only the original object can use to store and retrieve state in the memento. Design patterns also specify relationships between interfaces. In particular, they often require some classes to have similar interfaces or to place constraints on the interfaces of some classes. For example, both Decorator 175 and Proxy 207 require the interfaces of Decorator and Proxy objects to be identical to the decorated and proxied objects. In Visitor 331, the visitor interface must reflect all classes of objects that visitors can visit, specifying object implementations. So far we've said little about how we actually define an object. An object's implementation is defined by its class. The class specifies the object's internal data and representation and defines the operations the object can perform. Our OMT-based notation, summarized in Appendix B, depicts a class as a rectangle with the class name in bold. Operations appear in normal type below the class name. Any data that the class defines comes after the operations. Lines separate the class name from the operations and the operations from the data. Return types and instance variable types are optional since we don't assume a statically typed implementation language. Objects are created by instantiating a class. The object is said to be an instance of the class. The process of instantiating a class allocates storage for the object's internal data, made up of instance variables, and associates the operations with these data. Many similar instances of an object can be created by instantiating a class. A dashed arrowhead line indicates a class that instantiates objects of another class. The arrow points to the class of the instantiated objects. New classes can be defined in terms of existing classes using class inheritance. When a subclass inherits from a parent class, it includes the definitions of all the data and operations that the parent class defines. Objects that are instances of the subclass will contain all data defined by the subclass and its parent classes, and they'll be able to perform all operations defined by this subclass and its parents. We indicate the subclass relationship with a vertical line and a triangle. An abstract class is one whose main purpose is to define a common interface for its subclasses. An abstract class will defer some or all of its implementation to operations defined in subclasses, hence an abstract class cannot be instantiated. The operations that an abstract class declares but doesn't implement are called abstract operations. Classes that aren't abstract are called concrete classes. Subclasses can refine and redefine behaviors of their parent classes. More specifically, a class may override an operation defined by its parent class. Overriding gives subclasses a chance to handle requests instead of their parent classes. Class inheritance lets you define classes simply by extending other classes, making it easy to define families of objects having related functionality. The names of abstract classes appear in slanted type to distinguish them from concrete classes. Slanted type is also used to denote abstract operations. A diagram may include pseudocode for an operation's implementation. If so, the code will appear in a dog-eared box connected by a dashed line to the operation it implements. A mixin class is a class that's intended to provide an optional interface or functionality to other classes. It's similar to an abstract class in that it's not intended to be instantiated. Mixin classes require multiple inheritance. Class versus interface inheritance. It's important to understand the difference between an object's class and its type. An object's class defines how the object is implemented. The class defines the object's internal state and the implementation of its operations. In contrast, an object's type only refers to its interface, the set of requests to which it can respond. An object can have many types, and objects of different classes can have the same type. Of course, there's a close relationship between class and type. Because a class defines the operations an object can perform, it also defines the object's type. When we say that an object is an instance of a class, we imply that the object supports the interface defined by the class. Languages like C++ and Eiffel use classes to specify both an object's type and its implementation. Smalltalk programs do not declare the types of variables. Consequently, the compiler does not check that the types of objects assigned to a variable are subtypes of the variable's type. Sending a message requires checking that the class of the receiver implements the message, but it doesn't require checking that the receiver is an instance of a particular class. It's also important to understand the difference between class inheritance and interface inheritance, or subtyping. Class inheritance defines an object's implementation in terms of another object's implementation. In short, it's a mechanism for code and representation sharing. In contrast, interface inheritance, or subtyping, describes when an object can be used in place of another. It's easy to confuse these two concepts, because many languages don't make the distinction explicit. In languages like C++ and Eiffel, inheritance means both interface and implementation inheritance. The standard way to inherit an interface in C++ is to inherit publicly from a class that has pure, virtual member functions. Pure interface inheritance can be approximated in C++ by inheriting publicly from pure abstract classes. Pure implementation or class inheritance can be approximated with private inheritance. In Smalltalk, inheritance means just implementation inheritance. You can assign instances of any class to a variable as long as those instances support the operation performed on the value of the variable. Although most programming languages don't support the distinction between interface and implementation inheritance, people make the distinction in practice. Smalltalk programmers usually act as if subclasses were subtypes, though there are some well-known exceptions. Q92, C++ programmers manipulate objects through types defined by abstract classes. Many of the design patterns depend on this distinction. For example, objects in a chain of responsibility, 223, must have a common type, but usually they don't share a common implementation. In the Composite, 163, pattern, component defines a common interface, but Composite often defines a common implementation. Command, 233, observer, 293, State, 305, and Strategy, 315, are often implemented with abstract classes that are pure interfaces. Programming to an interface, not an implementation. Class inheritance is basically just a mechanism for extending an application's functionality by reusing functionality in parent classes. It lets you define a new kind of object rapidly in terms of an old one. It lets you get new implementations almost for free, inheriting most of what you need from existing classes. However, implementation reuse is only half the story. Inheritance's ability to define families of objects with identical interfaces, usually by inheriting from an abstract class, is also important. Why? Because polymorphism depends on it. When inheritance is used carefully, some will say properly, all classes derived from an abstract class will share its interface. This implies that a subclass merely adds or overrides operations and does not hide operations of the parent class. All subclasses can then respond to the requests in the interface of this abstract class, making them all subtypes of the abstract class. There are two benefits to manipulating objects solely in terms of the interface defined by abstract classes. 1. Clients remain unaware of the specific types of objects they use, as long as the objects adhere to the interface that clients expect. 2. Clients remain unaware of the classes that implement these objects, clients only know about the abstract class, ES, defining the interface. This so greatly reduces implementation dependencies between subsystems that it leads to the following principle of reusable object-oriented design. Program to an interface, not an implementation. Don't declare variables to be instances of particular concrete classes. Instead, commit only to an interface defined by an abstract class. You will find this to be a common theme of the design patterns in this book. You have to instantiate concrete classes, that is, specify a particular implementation somewhere in your system, of course. And the Creational Patterns, Abstract Factory, 87, Builder, 97, Factory Method, 107, Prototype, 117, and Singleton, 127, let you digest that. By abstracting the process of object creation, these patterns give you different ways to associate an interface with its implementation transparently at instantiation. Creational patterns ensure that your system is written in terms of interfaces, not implementations. Putting reuse mechanisms to work. Most people can understand concepts like objects, interfaces, classes, and inheritance. The challenge lies in applying them to build flexible, reusable software and design. Patterns can show you how. Inheritance versus composition. The two most common techniques for reusing functionality in object-oriented systems are class inheritance and object composition. As we've explained, class inheritance lets you define the implementation of one class in terms of another's. Reuse-based subclassing is often referred to as whitebox reuse. The term whitebox refers to visibility. With inheritance, the internals of parent classes are often visible to subclasses. Object composition is an alternative to class inheritance. Here, new functionality is obtained by assembling or composing objects to get more complex functionality. Object composition requires that the objects being composed have well-defined interfaces. This style of reuse is called black box reuse, because no internal details of objects are visible. Objects appear only as black boxes. Inheritance and composition each have their advantages and disadvantages. Class inheritance is defined statically at compile time and is straightforward to use, since it's supported directly by the programming language. Class inheritance also makes it easier to modify the implementation being reused. When a subclass overrides some But not all operations, it can affect the operations it inherits as well, assuming they call the overridden operations. But class inheritance has some disadvantages, too. First, you can't change the implementations inherited from parent classes at runtime, because inheritance is defined at compile time. Second, and generally worse, parent classes often define at least part of their subclass's physical representation. Because inheritance exposes a subclass to details of its parent's implementation, it's often said that inheritance breaks encapsulation, SNY 86. The implementation of a subclass becomes so bound up with the implementation of its parent class that any change in the parent's implementation will force the subclass to change. Implementation dependencies can cause problems when you're trying to reuse a subclass. Should any aspect of the inherited implementation not be appropriate for new problem domains, the parent class must be rewritten or replaced by something more appropriate. This dependency limits flexibility and ultimately reusability. One cure for this is to inherit only from abstract classes, since they usually provide little or no implementation. Object composition is defined dynamically at runtime through objects acquiring refer-instances to other objects. Composition requires objects to respect each other's interfaces, which in turn requires carefully designed interfaces that don't stop you from using one object with many others. But there is a payoff. Because objects are accessed solely through their interfaces, we don't break encapsulation. Any object can be replaced at runtime by another as long as it has the same type. Moreover, because an object's implementation will be written in terms of object interfaces, there are substantially fewer implementation dependencies. Object composition has another effect on system design, favoring object composition. Over-class inheritance helps you keep each class encapsulated and focused on one task. Your classes and class hierarchies will remain small and will be less likely to grow into unmanageable monsters. On the other hand, a design based on object composition will have more objects, if fewer classes, and the system's behavior will depend on their interrelationships instead of being defined in one class. That leads us to our second principle of object-oriented design. Favor object composition over class inheritance. Ideally, you shouldn't have to create new components to achieve reuse. You should be able to get all the functionality you need just by assembling existing components through object composition. But this is rarely the case, because the set of available components is never quite rich enough in practice. Reuse inheritance makes it easier to make new components that can be composed with old ones. Inheritance and object composition thus work together. Nevertheless, our experience is that designers overuse inheritance as a reuse technique, and designs are often made more reusable and simpler by depending more on object composition. You'll see object composition applied again and again in the design patterns. Delegation. Delegation is a way of making composition as powerful for reuse as inheritance, Li 86, JZ 911. In delegation, two objects are involved in handling a request, receiving object delegates operations to its delegate. This is analogous to subclasses, deferring requests to parent classes. But with inheritance, an inherited operation can always refer to the receiving object through the thisMember variable in C++ and self in Smalltalk. To achieve the same effect with delegation, the receiver passes itself to the delegate to let the delegated operation refer to the receiver. For example, instead of making class window a subclass of rectangle, because windows happen to be rectangular, the window class might reuse the behavior of rectangle by keeping a rectangle instance variable and delegating rectangle-specific behavior to it. In other words, instead of a window being a rectangle, it would have a rectangle. Window must now forward requests to its rectangle instance explicitly, whereas before it would have inherited those operations. The following diagram depicts the window class delegating its area operation to a rectangle instance. A plain arrowhead line indicates that a class keeps a reference to an instance of another class. The reference has an optional name, rectangle, in this case. The main advantage of delegation is that it makes it easy to compose behaviors at runtime and to change the way they're composed. Our window can become circular at runtime simply by replacing its rectangle instance with a circle instance, assuming rectangle and circle have the same type. Delegation has a disadvantage: it shares with other techniques that make software more flexible through object composition. Dynamic, highly parameterized software is harder to understand than more static software. There are also runtime inefficiencies, but the human inefficiencies are more important in the long run. Delegation is a good design choice only when it simplifies more than it complicates. It isn't easy to give rules that tell you exactly when to use delegation, because how effective it will be depends on the context and on how much experience you have with it. Delegation works best when it's used in highly stylized ways, that is, in standard patterns. Several design patterns use delegation. The State, 305, Strategy, 315, and Visitor, 331. Patterns depend on it. In the state pattern, an object delegates requests to a state object that represents its current state. In the strategy pattern, an object delegates a specific request to an object that represents a strategy for carrying out the request. An object will only have one state, but it can have many strategies for different requests. The purpose of both patterns is to change the behavior of an object by changing the objects to which it delegates requests. In Visitor, the operation that gets performed on each element of an object structure is always delegated to the visitor object. Other patterns use delegation less heavily. Mediator, 273, introduces an objecto-mediate communication between other objects. Sometimes the mediator object implements operations simply by forwarding them to the other objects, other times it passes along a referencito itself and thus uses true delegation. Chain of responsibility, 223, handles requests by forwarding them from one object to another along a chain of objects. Sometimes this request carries with it a reference to the original object receiving the request, in which case the pattern is using delegation. Bridge, 151, decouples an abstraction from its implementation, if the abstraction and a particular implementation are closely matched, then the abstraction may simply delegate operations to that implementation. Delegation is an extreme example of object composition. It shows that you can always replace inheritance with object composition as a mechanism for code reuse. Inheritance versus parameterized types. Another, not strictly object-oriented, technique for reusing functionality is through parameterized types, also known as generics, Ada, Eiffel, and templates, C++. This technique lets you define a type without specifying all the other types it uses. The unspecified types are supplied as parameters at the point of use. For example, a list class can be parameterized by the type of elements it contains. To declare a list of integers, you supply the type integer as a parameter to the list parameterized type. To declare a list of string objects, you supply the string type as a parameter. The language implementation will create a customized version of the list class template for each type of element. Parameterized types give us a third way, in addition to class inheritance and object composition, to compose behavior in object-oriented systems. Many designs can be implemented using any of these three techniques. Parameterize a sorting routine by the operation it uses to compare elements. We could make the comparison. 1. An operation implemented by subclasses, an application of template. Method, 325, 2. The responsibility of an object that's passed to the sorting routine, strategy, 315, or 3. An argument of a C++ template or ADA generic that specifies the name of the function to call to compare the elements. There are important differences between these techniques. Object composition lets you change the behavior being composed at time, but it also requires indirection and can be less efficient. Inheritance lets you provide default implementations for operations, and let subclasses override them. Parameterized types let you change the types that a class can use. But neither inheritance nor parameterized types can change at runtime. Which approach is best depends on your design and implementation constraints. None of the patterns in this book concerns parameterized types, though we use them on occasion to customize a pattern C++ implementation. Parameterized types aren't needed at all in a language like Smalltalk that doesn't have compile time type checking. Relating runtime and compile time structures. An object-oriented program's runtime structure often bears little resemblance to its code structure. The code structure is frozen at compile time. It consists of classes in fixed inheritance relationships. A program's runtime structure consists of rapidly changing networks of communicating objects. In fact, the two structures are largely independent. Trying to understand one from the other is like trying to understand the dynamism of living ecosystems from the static taxonomy of plants and animals, and vice versa. Consider the distinction between object aggregation and acquaintance and how differently they manifest themselves at compile and runtimes. Aggregation implies that one object owns or is responsible for another object. Generally we speak of an object having or being part of another object. Aggregation implies that an aggregate object and its owner have identical lifetimes. Acquaintance implies that an object merely knows of another object. Sometimes a sequaintance is called association or the using relationship. Acquainted objects may it's easy to confuse aggregation and acquaintance, because they are often implemented in the same way. In Smalltalk, all variables are references to other objects. There's no distinction in the programming language between aggregation and acquaintance. In C++, aggregation can be implemented by defining member variables that are real instances, but it's more common to define them as pointers or references to instances. Acquaintance is implemented with pointers and references as well. Ultimately, acquaintance and aggregation are determined more by intent than by explicit language mechanisms. The distinction may be hard to see in the compile time structure, but it's significant. Aggregation relationships tend to be fewer and more permanent than acquaintance. Acquaintances, in contrast, are made and remade more frequently, sometimes existing only for the duration of an operation. Acquaintances are more dynamic as well, making them more difficult to discern in the source code. With such disparity between a program's runtime and compile time structures, it's clear that code won't reveal everything about how a system will work. The system's runtime structure must be imposed more by the designer than the language. The relationships between objects and their types must be designed with great care because they determine how good or bad the runtime structure is. Many design patterns, in particular those that have object scope, capture the distinction between compile time and runtime structures explicitly. Composite, 163, and Decorator, 175, are especially useful for building complex runtime structures. Observer, 293, involves runtime structures that are often hard to understand unless you know the Pattern. Chain of responsibility, 223, also results in communication patterns that inheritance doesn't reveal. In general, the runtime structures aren't clear from the code. Until you understand the patterns. Designing for change. The key to maximizing reuse lies in anticipating new requirements and changes to existing requirements, and in designing your system so that they can evolve accordingly. To design the system so that it's robust to such changes, you must consider how the system might need to change over its lifetime. A design that doesn't take change into account risks major redesign in the future. Those changes might involve class redefinition and reimplementation, client modification, and retesting. Redesign effects. Many parts of the software system, and unanticipated changes are invariably expensive. Design patterns help you avoid this by ensuring that a system can change in specific ways. Each design pattern lets some aspect of system structure vary independently of other aspects, thereby making a system more robust to a particular kind of change. Here are some common causes for design along with the design pattern, that address them. 1. Creating an object by specifying a class explicitly. Specifying a class name when you create an object commits you to a particular implementation instead of a particular interface. This commitment can complicate future changes. To avoid it, create objects indirectly. Design patterns, abstract factory, 87, factory method, 107, prototype, 117. 2. Dependence on specific operations. When you specify a particular operation, you commit to one way of satisfying a request. By avoiding hard-coded requests, you make it easier to change the way a request gets satisfied both at compile time and at runtime. Design patterns, chain of responsibility, 223, command, 233. 3. Dependence on hardware and software platform. External operating system interfaces and application programming interfaces, APIs, are different on different hardware and software platforms. Software that depends on a particular platform will be harder to port to other platforms. It may even be difficult to keep it up to date on its native platform. It's important therefore to design your system to limit its platform dependencies. Design patterns, abstract factory, 87, bridge, 151. 4. Dependence on object representations or implementations. Clients that know how an object is represented, stored, located, or implemented might need to be changed. When the object changes, hiding this information from clients keeps changes from cascading. Design patterns, abstract factory, 87, bridge, 151, memento, 283, proxy, 207. 5. Algorithmic dependencies. Algorithms are often extended, optimized, and replaced during development and reuse. Objects that depend on an algorithm will have to change when the algorithm changes. Therefore, algorithms that are likely to change should be isolated. Design patterns, builder, 97, iterator, 257, strategy, 315, template. Method, 325, visitor, 331. 6. Tight coupling. Classes that are tightly coupled are hard to reuse in isolation, since they depend on each other. Tight coupling leads to monolithic systems, where you can't change or remove a class without understanding and changing many other classes. The system becomes a dense mass that's hard to learn, port, and maintain. Loose coupling increases the probability that a class can be reused by itself and that a system can be learned, ported, modified, and extended more easily. Design patterns use techniques such as abstract coupling and layering to promote loosely coupled systems. Design Patterns, Abstract Factory, 87, Bridge, 151, Chain of Responsibility, 223, Command, 233, Facade, 185, Mediator, 273, Observer, 293. 7. Extending functionality by subclassing. Customizing an object by subclassing often isn't easy. Every new class has a fixed implementation overhead, initialization, finalization, etc. Defining a subclass also requires an in-depth understanding of the parent class. For example, overriding one operation might require overriding another. An overridden operation might be required to call an inherited operation. And subclassing can lead to an explosion of classes, because you might have to introduce many new subclasses for even a simple extension. Object composition in general and delegation in particular provide flexible alternatives to inheritance for combining behavior. New functionality can be added to an application by composing existing objects in new ways rather than by defining new subclasses of existing classes. On the other hand, heavy use of object composition can make designs harder to understand. Many design patterns produce designs in which you can introduce customized functionality just by defining one subclass and composing its instances with existing ones. Design Patterns, Bridge, 151, Chain of Responsibility, 223, Composite, 163, Decorator, 175, Observer, 293, Strategy, 315. 8. Inability to alter classes conveniently. Sometimes you have to modify a class that can't be modified conveniently. Perhaps you need the source code and don't have it, as may be the case with a commercial class library. Or maybe any change would require modifying lots of existing subclasses. Design patterns offer ways to modify classes in such circumstances. Application programs. If you're building an application program such as a document editor or spreadsheet, then internal reuse, maintainability, and extension are high priorities. Internal reuse ensures that you don't design and implement any more than you have to. Design patterns that reduce dependencies can increase internal reuse. Looser coupling boosts the likelihood that one class of object can cooperate with several others. For example, when you eliminated dependencies on specific operations by isolating and encapsulating each operation, you make it easier to reuse an operation in different contexts. The same thing can happen when you remove algorithmic and representational dependencies. 2. Design patterns also make an application more maintainable when they're used to limit platform dependencies and to layer a system. They enhance extensibility by showing you how to extend class hierarchies and how to exploit object composition. Reduced coupling also enhances extensibility. Extending a class in isolation is easier if the class doesn't depend on lots of other classes. Toolkits. Often an application will incorporate classes from one or more libraries of predefined classes called toolkits. A toolkit is a set of related and reusable classes designed to provide useful, general-purpose functionality. An example of a toolkit is a set of collection classes for lists, associative tables, stacks, and the like. The C++ IOStream library is another example. Toolkits don't impose a particular design on your application, they just provide functionality that can help your application do its job. They let you as an implementer avoid reseeding common functionality. Toolkits emphasize code reuse. They are the object-oriented equivalent of subroutine libraries. Toolkit design is arguably harder than application design, because toolkits have to work in many applications to be useful. Moreover, the toolkit writer isn't in a position to know what those applications will be or their special needs. That makes it all the more important to avoid assumptions and dependencies that can limit the toolkit's flexibility and consequently its applicability and effectiveness. Frameworks. A framework is a set of cooperating classes that make up a reusable design for a specific class of software. Do 89, JF 88. For example, a framework can be geared toward built-in graphical editors for different domains like artistic drawing, music composition, and mechanical CAD, VL90, JO 92. Another framework can help you build compilers for different programming languages and target machines, JML 92. Yet another might help you build financial modeling applications, B93. You customize a framework to a particular application by creating application-specific subclasses of abstract classes from the framework. The framework dictates the architecture of your application. It will define the overall structure, its partitioning into classes and objects, the key responsibilities thereof, how the classes and objects collaborate, and the thread of control. A framework predefines these design parameters so that you, the application designer/implementer, can concentrate on the specifics of your application. The framework captures the design decisions that are common to its application domain. Frameworks thus emphasize design reuse over code reuse, though a framework will usually include concrete subclasses you can put to work immediately. Chapter 2. A case study. Designing a document editor. This chapter presents a case study in the design of a "what you see is what you get" or WYSIWYG document editor called Lexi.1. We'll see how design patterns capture solutions to design problems in Lexi and applications like it. By the end of this chapter, you will have gained experience with 8 patterns, learning them by example. Figure 2.1 depicts Lexi's user interface. A WYSIWYG representation of the document occupies the large rectangular area in the center. The document can mix text and graphics freely in a variety of formatting styles. Surrounding the document are the usual pull-down menus and scroll bars, plus a collection of page icons for jumping to a particular page in the document. 2.1 Design Problems. We will examine 7 problems in Lexi's design. 1. Document structure. The choice of internal representation for the document affects nearly every aspect of Lexi's design. All editing, formatting, displaying, and textual analysis will require traversing the representation. The way we organize this information will impact the design of the rest of the application. 2. Formatting. How does Lexi actually arrange text and graphics into lines and columns? What objects are responsible for carrying out different formatting policies? How do these policies interact with the document's internal representation? 3. Embellishing the user interface. Lexi's user interface includes scroll bars, borders, and drop shadows that embellish the WYSIWYG document interface. Such embellishments are likely to change as Lexi's user interface evolves. Hence it's important to be able to add and remove embellishments easily without affecting the rest of the application. 4. Supporting multiple look and feel standards. Lexi should adapt easily to different look and feel standards such as Motif and Presentation Manager, PM, without major modification. 5. Supporting multiple Windows systems. Different look and feel standards are usually implemented on different Windows systems. Lexi's design should be as independent of the Windows system as possible. 6. User operations. Users control Lexi through various user interfaces, including buttons and pull-down menus. The functionality behind these interfaces is scattered throughout the objects in the application. The challenge here is to provide a uniform mechanism both for accessing this scattered functionality and for undoing its effects. 7. Spelling checking and hyphenation. How does Lexi support analytical operations? such as checking for misspelled words and determining hyphenation points. How can we minimize the number of classes we have to modify to add a new analytical operation? We discuss these design problems in the sections that follow. Each problem has an associated set of goals plus constraints on how we achieve those goals. We explain the goals and constraints in detail before proposing a specific solution. The problem and its solution will illustrate one or more design patterns. The discussion for each problem will culminate in a brief introduction to the relevant patterns. 2.2 Document Structure. A document is ultimately just an arrangement of basic graphical elements such as actors, lines, polygons, and other shapes. These elements capture the total information content of the document. Yet an author often views these elements not in graphical terms but in terms of the document's physical structure, lines, columns, figures, tables, and other substructures. Point 2 In turn, these substructures have substructures of their own, and so on. Lexi's user interface should let users manipulate these substructures directly. For example, a user should be able to treat a diagram as a unit rather than as a collection of individual graphical primitives. The user should be able to refer to a table as a whole, not as an unstructured mass of text and graphics. That helps make the interface simple and intuitive. To give Lexi's implementation similar qualities, we'll choose an internal representation that matches the document's physical structure. In particular, the internal representation should support the following: maintaining the document's physical structure, that is, the arrangement of text and graphics into lines, columns, tables, etc., generating and presenting the document visually. Mapping positions on the display to elements in the internal representation. This lets Lexi determine what the user is referring to when he points to something in the visual representation. In addition to these goals are some constraints. First, we should treat text and graphics uniformly. The application's interface lets the user embed text within graphics freely, and vice versa. We should avoid treating graphics as a special case of text or text as a special case of graphics, otherwise we'll end up with redundant formatting and manipulation mechanisms. One set of mechanisms should suffice for both text and graphics. Second, our implementation shouldn't have to distinguish between single elements and groups of elements in the internal representation. Lexi should be able to treat simple and complex elements uniformly, thereby allowing arbitrarily complex documents. The 10th element in line 5 of column 2, for instance, could be a single character or an intricate diagram with many sub-elements. As long as we know this element can draw itself and specify its dimensions, its complexity has no bearing on how and where it should appear on the page. Opposing the second constraint, however, is the need to analyze the text for such things as spelling errors and potential hyphenation points. Often we don't care whether the element of a line is a simple or complex object. But sometimes an analysis depends on the objects being analyzed. It makes little sense, for example, to check the spelling of a polygon or to hyphenate it. The internal representation's design should take this and other potentially conflicting constraints into account. We can represent this physical structure by devoting an object to each important element. That includes not just the visible elements like the characters and graphics but the invisible, structural elements as well, the lines and the column. The result is the object structure shown in Figure 2.3. By using an object for each character and graphical element in the document, we promote flexibility at the finest levels of Lexi's design. We can treat text and graphics uniformly with respect to how they are drawn, formatted, and embedded within each other. We can extend Lexi to support new character sets without disturbing other functionality. Lexi's object structure mimics the document's physical structure. This approach has two important implications. The first is obvious: the objects need corresponding classes. The second implication, which may be less obvious, is that these classes must have compatible interfaces because we want to treat the objects uniformly. The way to make interfaces compatible in a language like C++ is to relate the classes through inheritance. Chapter 3. Creational Patterns. Creational design patterns abstract the instantiation process. They help make a system independent of how its objects are created, composed, and represented. A class creational pattern uses inheritance to vary the class that's instantiated, whereas an object creational pattern will delegate instantiation to another object. Creational patterns become important as systems evolve to depend more on object composition than class inheritance. As that happens, emphasis shifts away from hard coding a fixed set of behaviors toward defining a smaller set of fundamental behaviors that can be composed into any number of more complex ones. Thus, creating objects with particular behaviors requires more than simply instantiating a class. There are two recurring themes in these patterns. First, they all encapsulate knowledge about which concrete classes the system uses. Second, they hide how instances of these classes are created and put together. All the system at large knows about the objects is their interfaces as defined by abstract classes. Consequently, the creational patterns give you a lot of flexibility in what gets created, who creates it, how it gets created, and when. They let you configure a system with product objects that vary widely in structure and functionality. Configuration can be static, that is, specified at compile time, or dynamic, at runtime. Sometimes creational patterns are competitors. For example, there are cases when either prototype 117 or abstract factory 87 could be used profitably. At other times they are complementary. Builder 97 can use one of the other patterns to implement which components get built. Prototype 117 can use Singleton 127 in its implementation. Because the creational patterns are closely related, we'll study all 5 of them together to highlight their similarities and differences. We'll also use a common example, building a maze for a computer game, to illustrate their implementations. The maze and the game will vary slightly from pattern to pattern. Sometimes the game will be simply to find your way out of a maze. In that case, the player will probably only have a local view of the maze. Sometimes mazes contain problems to solve and dangers to overcome, and these games may provide a map of the part of the maze that has been explored. We'll ignore many details of what can be in a maze and whether a maze game has a single or multiple players. Instead, we'll just focus on how mazes get created. We define a maze as a set of rooms. A room knows its neighbors, possible neighbors are another room, a wall, or a door to another room. The classes room, door, and wall define the components of the maze used in all our examples. We define only the parts of these classes that are important for creating a maze. We'll ignore players, operations for displaying and wandering around in a maze, and other important functionality that isn't relevant to building the maze. The creational patterns show how to make this design more flexible, not necessarily smaller. In particular, they will make it easy to change the classes that define the components of a maze. Suppose you wanted to reuse an existing maze layout for a new game containing, of all things, enchanted mazes. The enchanted maze game has new kinds of components, like door needing spell, a door that can be locked and opened subsequently only with a spell, an enchanted room, a room that can have unconventional items in it, like magic keys or spells. How can you change Create Maze easily so that it creates mazes with these new classes of objects? In this case, the biggest barrier to change lies in hard-coding the classes that get instantiated. The creational patterns provide different ways to remove explicit references to concrete classes from code that needs to instantiate them. If Create Maze calls virtual functions instead of constructor calls to create the rooms, walls, and doors it requires, then you can change the classes that get instantiated by making a subclass of Maze Game and redefining those virtual functions. This approach is an example of the factory method 107 pattern. If Create Maze is passed an object as a parameter to use to create rooms, walls, and doors, then you can change the classes of rooms, walls, and doors by passing a different parameter. This is an example of the abstract factory 87 pattern. If Create Maze is passed an object that can create a new maze in its entirety using operations for adding rooms, doors, and walls to the maze it builds, then you can use inheritance to change parts of the maze or the way the maze is built. This is an example of the Builder 97 pattern. If Create Maze is parameterized by various prototypical room, door, and wall objects, which it then copies and adds to the maze, then you can change the maze's composition by replacing these prototypical objects with different ones. This is an example of the prototype 117 pattern. The remaining creational pattern, Singleton 127, can ensure there's only one maze per game and that all game objects have ready access to it, without resorting to global variables or functions. Singleton also makes it easy to extend or replace the maze without touching existing code.